Hey everyone, and welcome. Have you ever found yourself just staring at a differential equation feeling completely stuck? Well, today, we're going to look at a super cool visual tool called a direction field. It actually lets you see the solution to a differential equation, even when you can't find a nice, neat formula for it. So let's dive in.
So, what do you do when you hit one of those differential equations that seems impossible to solve with the standard methods? This is a really common hurdle in calculus. But what if I told you the equation itself holds the key to understanding its solution, even without an explicit formula?
Because it turns out, even when a differential equation looks unsolvable, it's actually packed with hidden clues about the shape and behavior of all its possible solutions.
And here is the absolute key, the most crucial point. A differential equation, y prime equals f of x comma y, is literally telling you the slope of the solution curve at any single point x comma y you can think of. This means we can figure out the direction the solution is headed at any specific spot without needing to know the whole picture. So what happens if we calculate that slope at a whole bunch of points and draw a little line segment for each one? We get a direction field, which you might also hear called a slope field. Seriously, think of it like a weather map, but for equations. It shows you the currents or the flow that any solution curve has to follow.
Okay, so how do we actually make one of these things? They might look super complicated, but the recipe is surprisingly straightforward. Let's break down the process.
First up, you'll lay out a grid of points, kind of like a checkerboard. Second, for every single one of those points, you plug its x and y coordinates into the differential equation to find the slope m. Third, you draw a tiny little line segment at that point with that exact slope. And finally, you just repeat this process over and over until this amazing overall pattern starts to pop out. It's like connect the dots, but with slopes.
Now here's a little pro tip to make your life a whole lot easier. Look for isoclines. These are just curves where the slope is constant. For example, if you have y prime equals x, think about it. The slope is the same all the way down any vertical line. Finding these allows you to sketch out huge chunks of the field all at once. It's a total time saver.
All right, enough theory. Let's actually see what these fields look like in practice. We'll start with a simple, but really important, type of differential equation.
Our first example is y equals y minus 2. Now notice that the slope here only depends on y. This is called an autonomous equation. And look what happens. When y is greater than 2, the slope is positive, and all the little arrows point up. When y is less than 2, the slope is negative, and they all point down. And right at y equals 2, the slope is 0. Bam! A perfectly horizontal line.
The behavior this reveals is just fascinating. That line at y equals 2 is an equilibrium solution, and you can literally see that the other flow lines are being repelled by it. They're all getting pushed away. And we can see this just by looking at the picture. No need to solve the equation.
Okay, now let's look at y equals x. This time, the slope only depends on x. So what does that mean for our isoclines? Well, now they're vertical lines. At x equals -1, all the slopes are -1. At x equals 1, all the slopes are +1. The pattern is immediately obvious.
And this is where it all just clicks together so brilliantly. We know how to solve this one, right? The integral of x is x squared over 2 plus c, which is just a whole family of parabolas. And look, the direction field is sketching them all out for us. It visually confirms the calculus we already know.
All right, this is where direction fields go from being a neat visualization to being a seriously powerful predictive tool. We can use them to understand the long-term behavior of a solution, to see its future, if you will, without ever finding its formula.
So let's tackle a more complex problem. Consider the equation y prime equals y times y minus 3. We want to know what happens to a solution in the long run. Does it grow forever? Does it settle down to some value? The direction field holds the answer.
Now, to predict the path of one specific solution, we need a starting point. This is our initial condition. The solution passes through the point 0, 4. So let's imagine placing our finger on the map right at y equals 4 and seeing where the current takes us.
So how do we do that? We just figure out the slope right at our starting value. We plug y equals 4 into our equation, y minus 3. That gives us 4 times 4 minus 3, which is just 4. The slope is positive. That tells us our solution has to start by increasing.
So since the slope at y equals 4 is positive, the solution curve starts to move up.
And as y gets even bigger, that y minus 3 term is also going to get bigger, making the slope even steeper. The curve just keeps going up faster and faster. The conclusion? The solution that starts at 4 increases forever. Its limit is infinity. We just predicted its entire future from one simple calculation.
So, what's the big takeaway from all this? Direction fields are this incredible bridge between algebra and geometry. They take an abstract, complex differential equation and turn it into an intuitive picture that reveals the behavior of every single possible solution all at once.
And that leaves us with a final thought. We've just seen a direction field predict a solution's ultimate fate, but what else is hiding in these visual maps? What other complex behaviors, like oscillations or stability, can a simple picture reveal about the dynamic systems all around us? It's pretty amazing to think about.